In this section, we are going to learn another way that we can multiply two vectors together, and it is called the cross product, and that's because the symbol that we use to represent it is an X. Another term used often for cross product is vector product, and the result of a cross product is a vector that is orthogonal to the two original vectors. So this always has to be in 3 dimensions, because the only way that we can be orthogonal, remember orthogonal also means normal or perpendicular, the only way that we can be orthogonal to 2 other vectors simultaneously is if we shoot off in a 3rd direction. So these are always going to be 3-dimensional. And the reason that it's sometimes called a vector product is because the output of a cross product is a new vector. So the definition is kind of complicated, but I'm going to try to show you a shortcut. So let's assume we've got 2 vectors, v, which has components v1, v2, v3, and vector w, which has components w1, w2, w3. V cross W is a giant formula. We are going to calculate V2 W3 minus V3 W2, and that will give us the I component. And then subtract V1 W3 minus V3 W1 to get our J component. And then the last term is V1W2 minus V2W1, and that is our K component. So that is a really big, complicated formula. So in my opinion, it's much more convenient to use a matrix calculation to perform a cross product rather than having to memorize that formula. So if you remember from algebra class, at some point in time you learned about matrices, and you may have also learned how to calculate the determinant of a matrix. It is possible, though, that you never actually did 3x3 determinants by hand, which is what I'm going to show you here. And we're going to use something called cofactor expansion. So the way that we set up a cross product with a matrix, our first row in the matrix is always ijk. In the second row of that matrix, we're going to put the components from the first vector in our product, so v1, v2, v3. And then the last row is going to be the components from the second vector in the product, w1, w2, w3. So essentially what we're doing here is we are calculating the determinant of this 3x3 matrix using cofactor expansion. So I'm going to go through my ijk in the first row and just start with the first one I see. So I've got I. Now if you cross off I's row and I's column, what we're left with is a 2x2 matrix. And that 2x2 matrix goes over here next to our I. So V2, V3, W2, W3. And then we are going to go on to the next element in the first row. Let me get rid of some of this. If we move on to the second element in the row, the J, anytime you do cofactor expansion, you alternate your signs. So I is a positive, J is going to be negative, and then we would go to K, it's going to be back to positive. If we mark off J's row and J's column and ignore it, what we're left with is these two element columns, which we're going to combine and make another 2x2 matrix. So we've got V1, V3, W1, W3. And then we'll move to our last element in the first row, which is the K. And if you mark off K's row and K's column and just look and see what's left, we've got this 2 by 2 matrix here. So we are going to put that over next to the K. So V1, V2, W1, W2. So to calculate these 2 by 2 determinants, we calculate the product on the major diagonal and then subtract the product on the minor diagonal. And we're going to do that for all of them. So the major diagonal starts at the top left, and you want to do that one first. So if we expand this out using determinants, we're going to have V2 times W3 minus the other diagonal would have a product of V3 W2. And we're going to do this for all of them. So the next one's minus J, and we've got V1 W3 minus V3 W1. Last term is K, and the determinant for that 2 by 2 would be V1 W2 minus V2 W1. Now, if you compare this to what I gave you above, it is exactly the same. The only difference is we didn't have to memorize this giant formula. We just had to know how to do a 3 by 3 determinant. So either way, whether you prefer to memorize that formula or learn how to do this 3 by 3 determinant matrix, doesn't matter to me, whichever way you're most comfortable with. Both of them will give you the exact same thing. I like even though I know the formula and I've memorized the formula, I really like the matrix way to do it. It doesn't seem so daunting having to memorize so much. So let's just try one basic example. We are going to find the cross product of vector V, which has components -2, 3, 4, and vector W, which has components 3, 7, 2. So I'm going to set this up as a 3 by 3 determinant matrix. So V cross W is IJK, -2, 3, 4, and 3, 7, 2. And then we need to expand this. So just like we did above, I'm going to go through the first elements, or the elements of my first row. So I've got I, and the 2 by 2 matrix that goes with that. You've got to mark off I's column and I's row, and you're left with 3, 4, 7, 2. And then change sign and do your J. Mark off J's row and J's column, and you're left with -2, 4, 3, 2. Change sign again to move to your K. Mark off K's column and K's row, and you're left with -2, 3, 3, 7. And now we just have to do the diagonal products and subtraction here. So for I, if you do your major diagonal, you get 6. Minor diagonal, you get 28. For J, major diagonal is -4. Minor diagonal is 12. And then for K, major diagonal is -14. Minor diagonal is 9. And it's always subtraction in those determinants. So this is going to give us a final answer of -22i. And then we've got a -16 in the parentheses, but if we combine that with the negative we have here for subtraction, it's really going to be plus 16j, and then minus 23k. So this vector, if we were to draw these, would make a 90-degree angle both with -2, 3, 4, and it would make a 90-degree angle with 3, 7, 2. We'll do some more examples and try some different things, but first, to kind of understand cross product a little bit better, we're going to go through some of the algebraic and geometric properties of cross product, see what kind of things we can do with them and what they are useful for. So for the algebraic properties, let's just assume that u, v, and w are vectors. And let C be a scalar. So one thing that you may notice right away as you start doing some examples, if you calculate the cross product of u and v, if you look at this formula, our formula involves multiplication, which we can do in any order we want and we would get the same answer. But it involves subtraction. So if we were to change the order of the subtraction, it's going to change the sign of our answer. So if you were to calculate u cross v, you will get the exact opposite of v cross u. All of the numeric values would come out the same, but they would all have the exact opposite sign. What this means is that cross product is not commutative. You can't change the order and get the same answer. And that's because our formula involves subtraction. It is, however, distributive. If you had u crossed with v plus w, remember, cross product is a type of multiplication, so we technically could go ahead and distribute the u and do those cross products individually. Cross product is quite a bit of work though, so I don't see typically how expanding that would be useful, but I could see how maybe condensing it would be useful. So using the equation in that direction. If I see that I've got two operations that both involve a cross product with the same vector, I could really just combine them so that I only did one cross product. So it is distributive. It is associative with scalars. So if I had a scalar being multiplied by a cross product, we can't change the order of the cross product, but we can decide when that scalar is going to be introduced. So we could do the cross product first and then multiply through the scalar. We could decide to multiply the scalar into the u vector and then do the cross product. And we can also decide to multiply that scalar into the v vector and then do the cross product. No matter where we decide to incorporate that scalar value c, we would get the same answer. As long as we don't change the order of the cross product, u always has to come first and v second. If you cross any vector with 0, you're going to get 0. So we've got a zero product identity. If you cross any vector with itself, you're going to get 0 as well. And that's because in order to concretely define a new orthogonal vector, you have to give two unique vectors into the cross product. And if you don't put two unique vectors into that cross product, you can't get a normal vector. So any vector crossed with itself would equal 0. And the same is true if you just crossed a vector with something parallel to it. So this is also true for parallel vectors. And then finally, this one is interesting. It involves three vectors inside of a product. It's very similar to property number 3, but we had a scalar and a cross product. This time, we've got a dot product and a cross product. So dot products and cross products are both considered to be multiplication, and we are allowed to use an associative formula on this to rearrange it. Associative formula, or the associative property, just allows us to change who's inside the parentheses. We can't actually change the order of the vectors. But something happens here when you change the order of the operations that we're going to perform, because the answer to a cross product is another vector, and then if you're going to do a dot product, you need two vectors. So if I was to move the parentheses so that they were around the u and the v, I can't keep that as a dot product, because u dot v would be a scalar, and then you can't cross a scalar with a vector. So we can move the parentheses as long as we also move those operations. We have to first come up with a new vector, because the dot product must be between two vectors. So it's how we can use the associative property. We do have to be careful though with which operations we're doing and what kind of answers we get back from them. This u dot v cross w is called the triple scalar product, and we will talk about it towards the end of this section. Some geometric properties, which will probably be a bit more useful, especially as some of this information in Calculus 3 overlaps with some things you may be learning or have learned in physics. Let u and b be vectors, and theta be the angle between u and v. So these properties are more about things that are going to happen on a graph. So the first property I have already talked about in the definition, or in the introduction for cross product. U cross V is a vector that is orthogonal to both U and V. And orthogonal just means normal is another word we use there, or perpendicular. It means they make a 90-degree angle. The very first formula I gave you for cross product, you could think of this as like an algebraic formula. It involves just a whole bunch of algebra calculations, and it also requires that our vectors be in component form. There is a geometric formula for cross product as well, because in a lot of application problems, especially in physics, vectors are not always going to be given to you in component form. They're typically given using magnitude and direction. So another way we can do cross product, or at least the magnitude of our cross product, just the magnitude of our cross product has special meanings in a lot of different areas of science. The magnitude of U cross V is equal to the magnitude of U times the magnitude of V times sine of theta, which we said is the angle between them. So this, I consider this more of a geometric formula, because it's gives us the information that we would use to graph. We know magnitude of U, magnitude of V, angle between them. It's a typical way to graph vectors. Then we could use that information to calculate at least the magnitude of the cross product. This next one I also talked about a little bit above in the algebraic properties. If U cross V equals 0, that is only going to happen if U and V are parallel. And we've talked about parallel vectors before, and that means that one is a scalar multiple of the other. So they point in the exact same direction. One's just longer and the other is shorter. Last property, geometric property, the magnitude of U cross V is the area of the parallelogram that has U and V as adjacent sides. So if you remember back a few sections ago, when we were adding vectors, one way we learned to do that was through the polygon method, or the parallelogram method. So if we were to take U and V and draw a parallelogram with them, we used that in order to find the sum. We said the sum was the diagonal, but that parallelogram we're drawing, we could easily find the area of that parallelogram by doing magnitude of the cross product. So let's say that's vector U and here's vector V. When we do parallelogram method, we would make a parallelogram with them to figure out the sum, which is the diagonal. But what this cross product does is it calculates that area. So a bunch of different things that will help us with calculations and also figuring out how we can use this cross product to help us. Let's try a few more examples. Let's find a unit vector that is orthogonal to both V, which is 2i minus 3j plus k, and W, which is I minus 2j plus k. So there's several things we're being asked to do here. We're being asked to find a unit vector that is orthogonal. Anytime you need a vector that is orthogonal or normal or perpendicular, you should think cross product. Every time you see this word in a problem using vectors, we should think of cross product. Now, there's no point in changing V and W to unit vectors because it doesn't guarantee the cross product will be a unit vector. The unit vector part we'll deal with at the end. We can take any vector and change it into a unit vector just by dividing by its magnitude. So that part we'll deal with at the end. But first, let's do our cross product so that we can find a vector that is orthogonal. So I'm just going to set up my 3x3 determinant matrix. That is my preferred way of calculating these. So first I start with my V components, 2, negative 3, 1, and then my W components, which are 1, negative 2, 1. As you do more and more of these, you will see that you don't necessarily have to write out every single step. I very often skip writing the 2x2s because I can see them here in my 3x3 matrix. So for I, I'm going to have negative 3 minus negative 2. Those are my two products. For J, I'm going to have 2 minus 1. And then for K, I'm going to have negative 4 minus negative 3. So our normal vector is negative I minus j minus k. All the components are negative 1, and that's just a coincidence. So the orthogonal part is done. Now we need to make it a unit vector. So the way that we calculate a unit vector is just by finding the magnitude of our vector and dividing all the components by it. So the magnitude for this new V cross W vector that we've just created, that's just the typical magnitude formula, which is the square root of the sum of your components squared. And this comes out to be square root 3. So I just need to go in and divide all my components by square root 3. So we're going to have negative 1 over square root 3i minus 1 over square root 3j minus 1 over square root 3k.